Our journey through the world of molecules is almost at an end. We have covered a lot of ground in the past 8 modules, starting with elementary particles, then progressing through atoms to molecules, then to molecular shapes with pauses to appreciate the role that electrons play in molecules and the beauty that arises from symmetry and chirality. In the last couple of modules, we've also observed how important interactions between molecules can be and how metals can contribute to critical functions in our bodies. What else could be left? Well, before we finish, we have one more important stop to make in the realm of ordered solids. The carbon framework molecules at the center of most of this course are representative of disordered materials. They form the basis for paper, leather, textiles, and other products that we derive from living things. However, there is a vast number of inanimate substances that are primarily found in nature as ordered materials, including salts, pure metals, most minerals, and even some smaller organic compounds like sugar. What could these materials possibly have in common? In Module 9, we will consider the atomic level structure of these materials and examine the ways in which these ordered solids are similar and the ways in which they are different. Our treatment of ordered solids starts with a consideration of how we can pack atoms together in the most space-efficient way possible. This is directly applicable to the atomic level structure of metallic solids. It turns out that a famous mathematical problem involving efficient ways to stack spheres is at the heart of this subject, and our discussion will help us introduce concepts that are common to all ordered solids. All I can say is Marie Kondo would be very proud of our ability to stack spheres so neatly. The sphere packing work will come in handy, as it is also the basis for the microscopic structure of ionic compounds, though with some interesting twists. These solids also give us a chance to talk about lattice defects, basically places in the solid where the order is disrupted. While this may seem to ruin a perfectly good ordered solid, it's also true that these defects can introduce new properties to the solid. You will have the opportunity to see several video simulations that show how the atoms in these solids are packed together. A few elements, notably carbon and silicon, are capable of forming a special kind of solid called a covalent network solid. These materials have very useful technological properties, and our modern lifestyle would be quite different without them. Imagine life without a cell phone or a computer or any number of useful pieces of technology based on silicon chips. Silicon also forms durable covalent network materials in combination with oxygen, including quartz, sand, and glass, which actually are really the same thing. We'll finish up by considering the weakest member of the ordered solid family, molecular solids. These are the crystalline substances generally comprised of small nonmetal compounds that are held together by intermolecular interactions. Even though these solids do not account for many industrial applications, their existence paves the way for us to learn about their bonding structure experimentally, simply by shining light on them. Well, okay, it's really X-ray radiation, but that is light of a sort. Ordered solids provide entry into the study of both geological minerals and industrial materials, and are even found in interstellar space. I bet you didn't know that. There's a lot of good stuff to learn, so let's get started.